projects or anything like that. Hash maps and hash sets are really, really useful. And to start with, I'm going to be focusing on the application of these rather than the implementation, because it's much more important to know how to use these than it is to actually implement them. We already talked about sets and maps earlier, specifically the ones that are implemented with binary search trees. Now, I talked about how sets are just kind of a set of values like 1, 2, 3, whereas maps are a little bit more complicated. That is kind of a set of keys, which are then mapped to a different value. We gave the example of like a phone book where some name is mapped to, the phone number. Number 1, 2, 3, something like that, right? So we're primarily going to be focusing on maps because they are generally more common and they're a little bit more complex, but the main ideas behind a map are nearly exactly the same as a set. Instead of just having like a set of keys, we're going to have that set of keys, except each key is going to be mapped to some separate value. But the key is what's used to sort the binary search tree. It's also what's used to access values from the hash set or the hash map. First, let's compare tree maps and hash maps though. There are typically three main operations you want to do when you have a map. You want to insert. When it comes to tree maps, the big O time complexity is log n to insert into that tree. That's definitely better than maintaining a sorted array, because inserting into a sorted array in the worst case would be big O of n. Removing from the tree is the exact same. It's also log n. Likewise with searching, we essentially run binary search on the tree map and we can search for any value in log n time. That's pretty good. And there are other bonuses of tree maps because they're ordered. We can iterate through it in sorted order. If we have that tree map, we can iterate through it in sorted order in O of n time. So that's like our in order traversal. Just by having a tree map, we are kind of maintaining that sorted order. With a hash map though, things get interesting. Inserting is actually a constant time operation. Removing is also a constant time operation. And searching is also a constant time operation. So you can already see why hash maps are probably the most useful data structures you're ever going to use. They really just beat tree maps out of the water. But there's a bit of a caveat here that this is actually not the worst case time complexity. Even though I'm writing it as big O, which means worst case, hash maps actually don't have this as the worst case time complexity for these three operations. This is actually the average case time complexity. But the vast majority of the time, people still assume that it is the worst case time complexity. So we write it as big O of 1. Like if you're ever doing a coding interview, it's safe to assume that these operations run in constant time. That's what people assume in jobs and just in general. I think if you ask them, most people don't actually know that these operations are actually average case. In the worst case, inserting, removing, and searching actually could be O of n time depending on how you implement the hash map, but that's not so important. important, and we'll actually touch on that a little bit later. Now, the downside of hash maps, and there's always a downside when you have something this good, it's that hash maps don't maintain any kind of ordering, actually. So if you wanted to iterate through all the keys of the hash map, you could not do it in O of n time. You'd basically have to take all of the keys and then sort them, and then depending on what sorting algorithm you use, you could use, merge sort, you could even use a binary tree sort. It would be n log n typically, though. So that's sort of the downside, but you can see that the positives definitely outweigh the negatives, especially if you don't need to traverse it in order and you just need to insert, remove, and search, which is what we would probably do with a phone book. Then hash maps are very important. So let's take a look at a common use case of hash maps. Let's say we were given a list of names, maybe in the form of an array, and we want to count for each name how many times does it show up in this array. So how would we use a hash map to do that? Well, the obvious way would be to map every single name, so use that as the key, and the value in this case will be an integer with the count of that name. So initially our hash map is going to be empty. We start at the first name, it's Alice, so we go ahead and add Alice to our hash map. But before we would even do that, what we could do is run search on our hash map. We would check, is Alice already in the hash map? No, it's not. And remember, search will run in constant time. So it's not in the hash map. So when we do insert it into the hash map, we should put the value 1 because this is the first time we're seeing this name. Next, we would go to the next position. By the way, for us to have done that, for us to have gone through one position, we did it in constant time. If we were doing it with a tree map, in the average case, that would actually run in log n time. I mean, we know that inserting a node into an empty tree is probably going to be O of 1, but in general, it's going to be log n. So now we're going to get to the second name, Brad. We're going to search for it in our hash map. That search is going to be O of 1. It doesn't exist. So we're going to do the same thing with Brad. We're going to add it as a key, and the value initially is going to be 1. We're going to get to the third one. We're going to get to the third name, Colin, do the exact same thing. Colin is also now added to the hash map. The value, the count of it is 1. Now we're going to get to our first duplicate, Brad. We've already seen Brad, so when we search our hash map, we're going to find that it already exists in the hash map. And it's at this position. So instead of assigning 1 here, we don't know. The count could be anything. Right now it's 1. It could have been 2. It could have been 3. It could be some value. We know it's not going to be 0 though. So what we should do here is instead of assigning it to 1, we should add 1 to it, which would put it to be 2. So we overwrite that value with a 2. By the way, doing that, iterating through this position was also a constant time operation. And notice we don't have duplicates in this hash map. I mean, we could have added another entry for Brad and put 1 here, but that isn't what we're trying to do. For Brad, we're trying to count how many times did it show up. It doesn't make any sense to add a second entry. And this brings us to a property of hash maps. They cannot contain duplicates. Duplicates are not allowed in hash maps because it doesn't really make sense for us to do that. That's not the use case for a hash map. Why would we want multiple copies of the same thing? And that's the exact same with binary search trees. Remember, we don't allow duplicates in binary search trees, so a tree map is also not allowed to have duplicates. So now let's go to the next position, Dylan. It doesn't exist in our hash map. We figured that out by searching, which is an O of 1 operation. So we add Dylan to the hash map, and the count is going to be initially assigned to 1. We get to the last person, Kim, and they also are not in the hash map. We add Kim and then set the count to be 1. Now for each position in the input array, we basically did a few O of 1 operations. So that means to have gone through this entire array and built this data structure, it would have been an O of n time algorithm. Now also the space complexity would also be O of n because in the worst case, every single name could have been unique. That would have led the size of our hash map to have been O of n. But this is definitely better than using a tree map. A tree map would have had the same amount of space, roughly speaking, it would have been O of n, but The time complexity for each one of these insertions and searches would have been a log n operation, and we know we have n values in the input, so the overall time complexity would be n log n with a tree map if we were doing it. But now we have a hash map. Hash maps are much more efficient. By the way, the code for this type of algorithm using a hash map would look something like this in Python. Suppose we're given an input array, names, and the same exact names that we have listed up here. We create our hash map. This is how you do it in Python. It's a little bit different than most languages, but in most languages you would declare like a hash map data structure with like a constructor or something like that. We're calling it count map. Then we're going through every single name in our list of names. And remember, we have two cases if count map does not contain this name. Now, in Python, the syntax for that is like this: if name not in count map, but most languages will have a count map data structure, and that will have a method or function which is called, let's say, contains, and then you'd pass in this key as the parameter to that method call. But basically we're checking this name does not exist in this count map, therefore we're going to assign that name to have an initial value of 1. The else would be that the name already exists in the count map, therefore we would increment that count by 1 like we did for Brad. So it's a pretty straightforward algorithm. It runs in linear time. Next, let's talk about how we can actually go about implementing a data structure like this. Now let's talk about the implementation of a hash map. Now most likely you'll probably not be asked to actually implement a hash map in an interview. It's pretty rare that you have to do that. And the implementation of hash maps can get really, really complicated. We'll be talking about the general concepts, and then we'll be coding up a relatively simple hash map. But I think the concepts are what you should really focus on, because the concept of hashing and the other ideas we're going to be talking about definitely come up in software in general. So this is definitely not the last time you're going to be hearing about these ideas of hashing, key value pairs, and things like that. First of all, under the hood, a hash map is actually implemented with an array. So in this case, we'll have some index, and that index will be mapped to the key value pair. And just because we have an empty hash map right now does not mean the size of our array is zeroed. Even an empty hash map is going to be non-zero. In this case, let's say we have an empty hash map, but our array is of size 2. We have index 0 and index 1. Now, the actual key value pair in this case, suppose it's just null, right? Some kind of default value, it's empty. We're basically indicating that we don't actually have anything stored here just yet. Now, with an empty hash map, the first thing we would probably want to do is start inserting some values. But how does an insertion actually work? In this case, let's say we're calling it put. It could be called insert or something like that. In this case, the key value is going to be a string, and the value itself is also going to be a string. That doesn't necessarily have to be the case. You know, this could be an integer, or this could be an integer, or they could be some other type. It could actually even be an object. But what's important here is that we have a way to convert the key. We don't care so much about the value, but the key should be able to be converted into an integer. And how we're going to do that is called hashing. We're going to have some kind of hashing function which is going to take the key value and then convert it into an integer. And when we have that mapping, you can see where I'm going. We're going to use that integer as the index, and that's how we're going to decide where to put that pair, that key value pair, into our array. So in this case, this array is actually an array of objects where the object itself is a pair, a key value pair. Well, the simplest thing would be able to map each character to some integer. For example, the first character A could be mapped to 0. I think L is the 12th character, so that could be mapped to the integer 11, and we could do that for every single character, and then we would add them up, and we would get some big integer. Let's just assume that the integer we get is a 25. I'm just making that up, but the idea is that we converted each character to an integer, then added them all up, and we got another integer, 25. Now, the only problem here is our array is only of size 2, so this is not really a valid index for our array. How can we fix that? Well, this is where a little bit of math is going to come in. We can take any integer, no matter how big it is, as long as it's positive, and we can take it and then mod it by the size of our array. So in this case, mod it by 2. If you're not familiar with modding, we're basically dividing 25 by 2, and we're getting the remainder that's left over. So in this case, 24 divided by 2 would equal 12 with a remainder of 1, because 2 can keep fitting into 25 until we get to 24. And then if we add a 2, we're going to get to 26. So that's too big. With 24, we have a remainder of 1 left over. Now, if we instead of 25, we actually had 24 and we were modding it by 2, then we would have a remainder of 0, because 2 does fit into 24 perfectly 12 times, and then we're left with a remainder of 0. And those are really the only two possibilities. But what's important to notice here is that when you mod by the length of the array, no matter what integer you're modding, you're always going to get a valid index as the output. The result that we get would always be a valid index if we're modding by the size of the array, which in this case is 2. It could have been 3, it could have been 4, but the mod is always going to result in a valid index. And the reason behind that is pretty simple. no matter what integer we're modding by, it could have been 5, the result, the remainder, is always going to be less than 5 because the remainder always has to be less than 5. It always has to be less than the number we're modding by, because if it wasn't, then it wouldn't really make any sense, right? We can't say 25 modded by 5 is equal to 5 because we can still divide this by 5 and then get 0, right? So it's just a little bit of math, but that's the main idea. So we mod by the size of the array to convert any integer like 25 to a valid index. So modding this by 2 in this case would lead to 1. So then we'd say Alice is going to be inserted at index 1. So in this case, Alice is going to be at index 1. The key is going to be Alice, and the value is going to be the city that she lives in, which let's say is New York City in this case. Now we're going to insert a couple more values, but suppose we wanted to first get Alice. We could do that in O of 1 time. We call get on Alice. We would, using our exact same hashing function, take Alice, convert it to an integer. Let's say again it's 25, mod that by 2, then we get 1. So in constant time, we were able to get the index that Alice is stored at. Then over here, we could go to that index and then say, okay, what city does Alice live in again? Well, it's New York City. So that's the idea, and that's why it's so efficient. Now, we're going to run into a few problems though. Let's say we now want to add Brad to the hash map. Let's say we convert Brad to some integer, right? Taking the sum of the characters. And by the way, when we actually convert a character to an integer, most likely we're going to be using the ASCII representation of the character. There are more complicated ones, but if you're using a set of 128 characters, so if we had a relatively small alphabet size, we could do this. Basically, it's a way of converting each character into a integer. And in that case, capital letters are actually different than lowercase letters. Like, for example, capital B could be evaluated to like 70. Lowercase b could be something like 44. But that's not so important. Let's just assume that we have a way to convert each character to some integer. But let's say we took Brad and the integer that it turned out to be was 27. Now we mod this by 2. We get 1 again. So what are we going to do? We're going to say, okay, at index 1, let's insert Brad. But Alice is already at index 1, so we can't really do that without losing the information we've already stored. This is a problem, and this is the problem with pretty much all hashing. It's something that you can't entirely avoid. It's called a collision. Clearly, it's bad to have collisions, but there are ways that we can work around it. We can minimize collisions and we can try to work around them, but we can't entirely get rid of them. That's really important to know. Hashing collisions pretty much always happen. Now, first, let's understand how we can try to minimize collisions. There's sort of a problem here. No matter what we convert Brad into, no matter what integer it gets converted to, modding it by 2 is either going to lead to a 0 or a 1. If our hash map is half full, like one of the spots is already taken, we basically have a 50-50 chance of having a collision or getting the position that's empty. Those aren't great odds. So typically what happens with hash maps is we keep track of the size of the array, and we keep track of how many keys are actually inserted into the array. In this case, the size of the array is 2, and we only have 1 key actually inserted in the array. So we say that the hash map is half full. And typically when it becomes half full is when we resize the array. And resizing the array actually works pretty much exactly the same as when we did it with dynamic arrays, meaning we take the size and roughly double it. And we would have done that not at the time that we're inserting Brad. We would have done that as soon as we inserted Alice. We inserted Alice, and then we realized our hash map is half full. So at that 3, so 4 elements now. But ignoring Brad for a few more seconds, what if now we try to get Alice? Well, we convert Alice to the integer 25. We mod it now. Instead of modding it by 2, we're actually going to mod by the size, which is 4. And it turns out that the index is 1 again. So we see that, okay, Alice is still in the correct spot. In this case, it works out, but it's not always going to work out. For example, what if instead of Alice being a 25 was a 27? In that case, when we mod it by 2, it would have gone at index 1, exactly where it's still at. But then when we resize and we try to get Alice again, we try to search for it, we mod this by 4 now because the size has increased, and modding 27 by 4 leads us to 3. So we would say, okay, Alice is probably at index 3. We would check and we'd see that no, Alice is not there. What I'm saying here is when we resize the array, we can't just leave the values where they previously were because the size changed. Therefore, the index using our hashing function might have also changed. So what we have to do when we resize, we take every single key that's already in the hash map, we recompute the hash of it using the new size, and then move it to where it should now be. For Alice's case, 25 modded by, we're doing it when the size is half full and we're doubling it every time. It's still relatively efficient because it's going to be infrequent that we have to do this rehashing. Obviously, it's pretty expensive because we're going to have to go through every key that's in our hash map. But as long as we double it the same way that we did with a dynamic array, it's going to be relatively efficient in the average case. So now finally, let's get back to Brad. Instead of modding it by 2, now that our hash map is size 4, we're going to be modding this by 4. 27 modded by 4 is 3. So in this case, we don't have a collision. And it makes sense because our chances of a collision have definitely decreased. We have a bunch more empty positions. So Brad is going to go over here, and the city that Brad lives in is Chicago. And since once again our hash map is half full, we're going to again resize it. So we would double the size. So now it would be of size 8. I'm not going to draw out the whole thing because it's not super important, but let's just assume that the size of this has now become 8. This will help us minimize the chance of a collision, but we're going to insert one more person now, Colin. Let's assume that after hashing the name Colin, we get an integer value of 33. We mod that by the size of our array now, which is 8. We mod that by 8. We get a remainder of 1. So even though we tried to minimize the chance of a collision, which is good, sometimes we still run into the case where we have a collision. We are going to insert Brad or Colin at index 1, even though Alice is already there. And by the way, when we resized this from 4 to 8, we would have actually had to recompute the position for each of these and then potentially moved it to that position. So for Alice, since I think Alice was 25, that was the hash of Alice, and then we'd have to mod it by 8, which in this case would have been 1 once again. So Alice actually would have stayed exactly where they are. The hash of Brad was 27. We would mod that by 8, and that actually would have also been 3, exactly where it still is. That's mainly just a coincidence, to be honest. I didn't even plan that, but it's convenient for us because we don't have to redraw this now. How would we actually handle this now? I mean, if we really wanted to, we could resize the array and maybe that would decrease the chance of this being a collision, but it still might end up being a collision. So we need a different way of handling collisions, and there are actually multiple ways of doing that. One way of doing it is actually at every index, instead of just storing a single pair, we actually store a linked list of pairs. So we could actually have multiple pairs occupying the same index. Now, the downside of that approach is we have to kind of maintain that memory and the pointers and all that. And when we actually run the get operation and we arrive at, let's say, index 1, we're looking for Colin, we would first see in the linked list, we'd have to traverse through the entire linked list. We'd first see Alice is there. That's not who we're looking for. We'd go to the next position in our linked list, and then we'd see, oh, Colin is over here. And then we'd return whatever value we're storing for Colin, which in this case is Seattle. But that's kind of the downside of, and that linked list approach is commonly referred to as chaining. There's another approach called open addressing, and it's called that is. So we can go in who actually does not exist in the hash map. Maybe we somehow computed the exact same index for Dylan. We would look at index 1. We'd see this is not Dylan. We would open address. We would try the next available address. Is Dylan over here? No, they're not. We'd try the next available address. Is Dylan over here? Nope. Is Dylan over here? Nope. And at this point, we know we can stop. We don't have to search through the entire index. First of all, that wouldn't be efficient. That would be O of n, and we definitely don't want to do that. But we know that if Dylan did exist, the hash of Dylan would be at 1, but this was occupied, so we would have put Dylan over here, but Dylan was not over there. So then we would have tried the next position. Dylan would have been inserted over here, but he's not there. And then we would have tried the next position over here, but this is empty. So if Dylan existed, he would have been here, but he's not. Therefore, Dylan does not exist in our hash map. This will make a little more sense if I explain how we would insert Dylan. So let's say instead of getting Dylan, we're inserting Dylan. Let's say hashing Dylan, we got the index 1. Then we try to insert Dylan over here. Well, this is occupied. So now we try the next available index. This is occupied. Next available, this is occupied, next available. Well, we're going to insert Dylan over here and whatever city that they happen to live at. So this is a sort of naive way of doing open addressing because we're just trying the next available position every single time. The downside of this approach is we're going to cluster the hash map potentially. If we have a really big hash map and we get a lot of collisions, all the keys are going to be stored close to each other. There are better ways of doing this open addressing. Instead of just computing the +1, maybe we take that value and square it and do other things with it. But the important thing to focus on here is that we have collisions and we have ways of handling those collisions. And there are, more optimal ways of handling that. And you could spend a lot of time learning about that. It's pretty math heavy, to be honest. So we won't go too in depth into it. And you likely won't need that kind of knowledge for coding interviews. But it's important to know that there are ways of handling things like this. Now, the last thing I want to mention before we actually take a look at a simple code implementation of a hash map is that when we maintain the size of the array, it's more optimal for the size to actually be a prime number. For math reasons, that ends up resulting in less collisions for the hash map. So typically, the size of the array is going to be a prime number. So if the size of it is prime and you're doing all these kind of crazy optimizations, that would be a very, very long interview question, and it's very unlikely you'll be asked that. Even if you are asked to implement a hash map, it's probably okay to do it a very simple way. That's why I'm going to be showing you the simple way to do it right now. So first, let's look at how we would kind of initialize our hash map. Like I said, we're actually going to be storing pairs in this array. This is one way to implement that. We have like a class, and that class will store 2 values. values, the key and the value of that pair. In our case, we were within the boundaries of that's okay. Is it non-null? Suppose we're searching for Alice and we get an index of 1. We would look here. It's non-null. So then we would check, bring us colon. This is Alice. So then neither of these execute. We just increment the index by 1 and modding it to make sure it stays in bounds. And then much on memorizing and why inserting, removing, and searching run